Okay, AP Calc BC, Unit 6, Day 3. You're going to take notes on your own paper today. I know, it's horrible. All right, Euler's method. This is a new technique, which is just taking it a step further of a technique we learned last year in AB. By the way, Euler is a German mathematician. I think that's how you say it. Or I don't know if you really want to, you call it Euler, or I don't know, but Euler. So let's talk about what we learned last year in Calc AB. There was a thing that we had to do quite a bit of called a tangent line approximation, or they might have called it a linear approximation. And the idea was, I'll kind of just draw a generic picture first, that you had a curve, and then you could draw a tangent line at a certain point, and it would be at some known point, which you might also call like an initial condition, right? And you could construct a tangent line. This was usually accompanied with a differential equation. That's why it's relevant. And you could use this line, like you knew this point was true, and you could use this tangent line and estimate another value on the curve further down. Now, this is the actual value, but we could use the tangent line's value as an estimate. And this difference here would be the error of your estimate, overestimate, underestimate. And the over underestimate has to do with concavity. So usually if you used points closer to the point of tangency, the better it was. The further you got away from it, probably the worse it was. So that's what today what we're going to be doing is based off that idea. So let's look at a problem where we just use this technique from last year. So we're going to start with a differential equation. Sometimes we call them DEs or DiffEQs. So we'll go ahead and practice this on an actual problem. Now, this is a problem that we can't integrate because we can't separate the variables. So it's a good one to do it on. We really have no shot at getting the exact answer. So that's the initial condition, and I want you to find the value at 2. Estimate. So what we do is we say, okay, well, let's create the tangent line. Let's get the equation of the tangent line to this graph at the known point 0, 2. And so we need a point, which we already have, and we need the slope. So the slope, dy dx, at 0, 2 is 0 plus 2 is 2. And then that's going to be your slope. This is your point, right? And we could write the equation in point slope form. Y minus 2 equals 2 times x minus 0. It might be helpful to change it to a differential, to a slope intercept form, because we're going to use it to calculate some things. So it'd be 2x plus 2. So this is our tangent line, right? And then we're going to say, okay, well, let's plug the point we want on the curve, but let's plug it into this tangent line, maybe like off here, and get the value of the tangent line. And that's going to be 6. This is the actual value of the y-coordinate on the tangent line. It's close, we're saying, to the value of the curve that the tangent line is tangent to. So that's called a tangent line approximation or a linear approximation. And this is what we did last year. We did it a bunch. And now what we're going to do, okay, so we're going to take this one more step. So we're going to do something called Euler's method. And Euler's method is really just a repeated use of the tangent line approximation. It's kind of based off the idea. And here let's see, we're gonna redo this, but with 4 steps. Okay. And over here, I'm gonna draw a little picture just to kind of illustrate the idea here. We have, say, the same curve, and we did a single tangent line, and we got the error, right? It was off. This was our estimate. So what we could do is, instead of taking this one giant step, okay, this is the known value, right? And this is the desired value. What we could do instead is estimate, break this up into, say, 4 equal steps, okay? And we say, okay, well, let's estimate this right here. We'll take that as our first estimate. And then let's write a new tangent line, okay? Now, it's going to be based off the fact that we think this point is close to being on the curve, but we got to use this slope right here, but it's going to be right there, okay? And we're going to take that as the next estimate, and then it'll take the slope here, and we'll write a new tangent line, and that'll be it. And we'll take the slope here, and we'll write a new tangent line, and that'll be it. So if we break this down into a bunch of individual tangent lines based off this estimation idea, but just do smaller steps repeatedly, the error is probably going to be a lot less. And I mean, the idea is, if we did this like 100 times, it'd be even better, right? And I feel like this is an idea that we've been using a lot in calculus. Like if you try and estimate the area under a curve with one slice, it's going to have a lot of error. But if you do 100 slices, the error gets smaller. And if you go to infinity, it goes to 0. So this is the same idea where we just break it into smaller steps and more of them to get a better estimate, okay? Now, let's look at how we do that. That was essentially what we did last year was a one-step Euler's method, okay? So Euler's method is saying, let's keep doing that. Let's break it into small steps. So we're going to do 4 steps. They don't have to be equal steps, but a lot of times they are equal step widths, equal steps, okay? Now, if you want to find the step size, you just find the distance between your desired point and the known point and divide by 4, right? If you want 4 steps, or however, divide by the number of steps. That'll give you the step size, right? So the step size is going to equal the distance between the x's, the x you know and the x you want, divided by the number of steps. So in this case, we're going from 0 to 2. So it's going to be 2 divided by 4 is, each step is going to be 1/2 or 0.5. Okay. Not that you could probably do that in your head. So let's do the first step. Now the first step is going to look just like what we did last year, essentially. We want to find, we have the point, right, 0, 2. You want to find the derivative. I'll just write it like this. The derivative at 0, 2. Plug it into the derivative equation that you have, that you were given. And you get 2, and that's your slope. So then you can write your tangent line, y minus 2 equals 2 times x minus 0. And you could rewrite it in slope intercept form if you want, y equals 2x plus 2. So you have your tangent line. And then instead of plugging 2 in like we did last year in one big giant step, we're going to plug in 0.5 and get an estimate earlier. And that's going to be 3. So this is an estimate for y 0.5. Okay, we're going to use this point to do another estimate, okay? So this will be our second step. So we got to do y prime again, but using this new point, 0.5 comma 3, using the same derivative we started with. We're doing it with this differential equation still. So it's x plus y. And so we get 3.5 for the slope of the tangent line. Then we write point slope form, y minus 3 equals 3.5 x minus 0.5. And then we could change it to slope intercept form. It's going to be y equals 3.5 x minus 1.75 plus 3 be plus 1.75. Oh, wait, no. Oh, no. 1.75. Negative 1.75 plus 3 would be 1.25. Okay, 1.25. So there's our tangent line. And now we're going to estimate it with the next point after 0.5 would be 1. 0.5 later. And this is an estimate, by the way. This is just a tangent line estimate. So it's going to be 4.75 is the estimate for y1. Okay, and then we're going to do it again. So, and to me, I don't feel like this is a confusing process. It's tedious. We're just doing a bunch of tangent lines. I'm using the next tangent line from the last one. So we need to do y prime at 1 comma 4.75. Plug it in the same differential equation that we've been using to get 5.75, which is our slope. And then we're going to write a tangent line, y minus 4.75 equals 5.75, x minus 1. And we're going to get y equals 5.75x minus 5.75 plus 4.75 would be minus 1. So that's our tangent line. And then we're going to estimate the next point, 0.5 further. We're working our way towards 2, right? In 4 equal steps of 0.5 each. So we're going to use this 5.75 times 1.5 minus 1 is, I'm just going to write, it's 7.625. So, I mean, one of the things about this is if we start getting decimals, they're kind of messy. Usually it'll probably work out nicer than this, but it's just a simple example. So we got last step, our fourth tangent line. Okay, so y prime 1.5, 7.625 equals 1.5 plus 7.625 equals 9.125. That's your slope. You're going to write another tangent line, y minus 7.625 equals 9.125 times 1.5, or times, x minus 1.5. We could change this to slope intercept form, y equals 9.125x. This is where it gets a little messier. I'm just going to tell you what it is, 6.0625. You don't want to get rid of any of your decimals yet. Do not round or truncate to 3 decimals in the middle of your work. So this is our fourth and final tangent line. And so then we're going to plug 2 into this to get our last estimate. So, I mean, this is going to be 18.25. So minus 6 is going to be 12.1875. I think I actually pulled that off in my head, even though I cheated on a couple others. So this is your final answer, okay? Your estimate for y2. So we estimated the same thing that we estimated last year with 1 step. We got 6. With 4 steps, we got 12.1875. I mean, that's a big difference, right? I feel like that's a big difference, okay? Now, this is a bit tedious. So you could do it like this. I feel like it's straightforward. You just got to be careful. It's tedious. You got to do a bunch of tangent lines. I mean, the work isn't like high level. It's just writing equations of lines and getting points and writing new equations of lines and getting points and writing new equations of lines. And it got a little messy too. There is sort of a shortcut way of streamlining the work. Okay, you do it the same work, but as I always warn you with any shortcuts, if you don't understand it, you better not use it, because I guarantee you're going to mess it up. It's going to be obvious that you don't know what you're doing, and I'm going to not give you any credit. It'd be better to do it this way and make mistakes in the work here and get a lot more credit than to use the shortcut wrong and probably get no credit. Okay? Now, keep this approach that we just did in mind to help you make sure you do the shortcut correct. I mean, that's your only hope. If you just straight out memorize it, I guarantee you're going to mess it up. And you're not going to remember it for long. So, we're trying to write the equation of a tangent line. So let's go back to that. Okay. And it's y minus some known y value, right? Equals the slope times x minus some known x value. So, I mean, this is just writing the equation of a line in point slope form anytime, right? So keep that in mind. Now, what we're going to do is we're going to use this to plug a new x in and get a new y out for our next estimate, our next step. So I'm going to rewrite this as y new minus y old previous. And the slope is going to come from the derivative at the last point. So we're going to calculate the derivative at the known x and y. That's what we were just doing in all that work, okay? Times x new minus x old, okay? So if you can do this, if you can think this through, then I think you have a shot at using the shortcut. If you can't, you have no shot. Now, I'm going to tweak this a little bit. I'm trying to find a new value for y at each step, right? So I'm going to move the old value to the left side by adding it. And that x new minus x old is going to be the same for every step if we're doing equal step sizes, right? So if we're doing equal step sizes, that's the step size, the distance between the current x and the previous x, okay? Then I'm going to call it, a lot of times we use this in math, delta x for a small step in x. I'm just going to call it delta x, and it's usually going to be the same throughout the problem. Now, if you get that, we can now make a table to sort of put this information in the table and kind of speed things up. It takes a little bit of the repetitive work out. I want an x and a y. For us, the initial condition was 0, 2, okay? So I want the x and the y first, and then the new y is going to be the next one below it, is going to equal the old y plus y prime, right, times delta x. So the new y is going to equal the old previous y plus delta y plus y prime plus delta x. So this is a way to just kind of organize it. So now we still got to find y prime ourselves by plugging it back into the derivative that we started with x plus y, which is going to be 2. And delta x we calculated was 0.5. So for every step of the way, we're going to go up 0.5, up 0.5, up 0.5, up 0.5. So we're going to do 4 estimates. Okay? Delta x is going to remain the same all the time. So you could just fill this in if you want. Okay? So plus this times this. I just kind of write this stuff in here. And if you just try and straight out memorize this table, it's going to be disaster. So go back and start with it. Write this stuff down to make sure the table makes sense to you. Every time you set it up, just to get the hang of it, make sure you know how to do it. And then a week later, when you haven't done it for a whole week, you might actually have a shot. Otherwise, you got to do it the old way, which to me, you should be able to remember too. But it's just a lot more work. This is just based off that. Now, This right here equals the old y above it plus the y prime from the old xy times delta x. So that's going to be 2 plus 2 times 0.5. That's going to be 3. And then we repeat the process. So we say, okay, we add these together to get y prime. And the next y is going to be the old y plus these. That's going to be 1.75. That's going to be 4.75. So we're doing the same work we did right here, but just sort of nicely condensed. So that's your new y. Okay, so we're going to add these together to get the new y prime. And this, we're only adding these because that's what this differential equation said to do. If the differential equation is different, you got to follow that rule. So now it's going to be this plus this times this. Okay, and that's where we get 7.625. So all right, got that. So now we add these together, 9.125. We're going to add this times that, and we're going to get 12.1875. This is your answer, okay? We don't need to do another y prime. We don't even need a new delta x. This is it. We're done. Okay, we did 4 of them right here. Now, you should write your final answer more nicely. Like f of 2 is approximately 12.1875. All right. So this table right here, that's how you could do it. Now, I'll probably show you on the homework. Maybe we could try 1 or 2 or something on today's homework, and so you can kind of get the hang of it. So this is a process we were doing last year with 1 step. Now we're breaking it down into smaller, more frequent steps. And so you have a short worksheet today. So you can do, your assignment is worksheet 6.3. All right. So, let's see if we can try these. Maybe I'll try one with you. That one looks a lot like the one we just did. So, I don't know. We can maybe we do number 2. Okay. Now, if you want to do that table approach, you got to be able to set it up. And to set it up, at least once on this assignment, I say, okay, well, I'm doing y minus y1 equals m times x minus x1. And this is the y old, and this is the x old that I already know. And this is the derivative at that x and y old. Okay? So this is y new, and this is x new. And then this is going to be delta x. So if I rewrite this, y new equals y old plus y prime at the old spot times delta x. You got to be able to do that if you're going to do this table. Okay, otherwise you're going to be doing that anyways, just a bunch of separate times. So the table, we want to keep track of the x and y pair as we go, and then we need y prime, and then we need delta x. Now this time we're starting at 5.5 and going to 4 with delta x is at 0.5 now. And so we're going forward now. Sometimes you could go backwards, and your delta x's would have to be negative because x new minus x old would be going backwards, would be negative, and you can totally do it. You can go. Usually we're kind of going left to right, but you could go right to left. Your delta x's would be negative. So how many steps are we going to take if we're going from 4 to 5.5? So they didn't tell us how many steps this time, but they told us the step size is 0.5. So you're going to start at 4, then you're going to go to 4.5, and then you're going to go to 5, and then you're going to go to 5.5. So this is going to be 3 steps of 0.5 to get from 4 to 5.5, right? And it's going to be plus this times this. Okay, so the first known value is 8, 4, 8. Plug in here, 2 times 4 is 8, plus 8 is 16. we're going to do this plus this times that. That's going to give you 16. That's the new y. All right. Then we got to do 2 times 4.5, which is 9 plus 16 is 25. This plus this times this. So that's going to be 12.5. That's going to be 28.5. Then we got to do 2 times this plus this. So that's going to be 38.5. This plus this times this. Old y, new y equals old y plus y prime times delta x. That's going to be 19.25. So that's going to be 47.75. And we'll write our final answer as F 5.5 is approximately 47.75. So let's write the answer nice. If you're going to use the table, let's write the answer down nice. So that's how you do it. On number 4, you're going to do the estimate. Then on part B, you're going to find the exact value by solving the differential equation like we've been talking about already for days. Okay. 5 and 6, the tables are already kind of set up for you, so you can use this. The one thing you got to do is add delta x, which you can totally figure out over here is 0.5. And it might be constant or might not be constant. So looks like it's constant 0.5, right? You don't need to worry about number 7. So try these out. Get good at this. Make sure you understand it. And if you're going to use the shortcut table, make sure you really understand how to set it up from scratch, not from pure memorization. That will not work here. And if that's what you're doing, it's going to be super clear to me because you're going to make tons of crazy, weird mistakes. And I'm just not going to give you any credit because you have no business using a shortcut if you don't know how to use it. And memorizing the shortcut is not going to be the way to go.